rolling. We're going to have a look at rolling. We're going to try and work out which one of these balls is going to roll the fastest. We've got a basketball that's hollow. This one here is squidgy. It's solid all the way through. Which one's going to roll the fastest? Which one will reach the bottom of the hill the quickest? Make a prediction.
Go on, actually stop the video and do it. Let's have a think about the theory of rolling for a moment. When something's rolling along the ground, that means there's constant friction between that object and the ground. It's not sliding, it's rolling. That means that it's got rotational velocity and it's got linear velocity. And it's really important for us to remember that we can connect rotational and linear velocity using V equals R omega. This means that the body is going to have two different sorts of kinetic energy at the same time. It's going to have linear kinetic energy, that's the familiar half mv squared, and it's also going to have rotational kinetic energy, that's the half I omega squared. Let's see how we can put those equations together to make some sense of it. As an example, let's start thinking about a solid sphere, the same material, right the way through, constant density, a ball. The equation for the inertia of a body like that is I equals 2/5 mr squared. So the first step you can see down there is we're going to plug into our rotational kinetic energy. Instead of I, we're going to put 2/5 mr squared. And then we're going to remember that we can connect linear and rotational motion with V equals R omega. So V squared is R squared omega squared, and therefore omega squared is V squared over R squared. We'll plug that into our equation, and you can see that it's now the half has cancelled the 2 out of the 2/5, so it's 1/5 mr squared V squared over R squared, and that just cancels to be 1/5 mv squared. So we've got 1/2 mv squared plus 1/5 mv squared. And a half plus a fifth is the same as 5/10 plus 2/10. That gives us 7/10 mv squared. So the really useful application of this, the why do we care, is for solving problems like a ball rolls down a ramp problem. We can see in this example, using conservation of energy, the ball starts up the top of the ramp with EP equals mgh, same as usual, but because it's rolling, not sliding, down the bottom of the ramp, the EK is 7/10 mv squared, like we just calculated. So then we just follow the process we're familiar with. We set that gravitational potential energy equal to the kinetic energy. It's the combined rotational and linear kinetic energy. Cancel off the m's on both sides, noticing that the mass of the rolling body, the ball, doesn't come into it, and end up with the V as the square root of 10 GH over 7 for a solid sphere. So here's an example that should help to shine some light on our little video problem from back at the start. A basketball and a cricket ball are released from the top of a ramp simultaneously, and the inertia of a basketball is 2/3 mr squared, and a cricket ball is a solid sphere, so it's 2/5 mr squared. So have a go at doing what we've just done and work out an expression for the kinetic energy of the basketball at the bottom of the ramp, and then work it through to try and puzzle out, will the hollow sphere or the solid sphere reach the bottom of the ramp first? Here's my working for the basketball. Really similar process to what we did for the solid sphere before. We end up with V is the square root of 6 GH over 5. Now we've just got to make a comparison. To make the comparison, I just evaluated the numerical part of the equation, so root 6 over 5, 1.1, and root 10 over 7, 1.2. That tells us that the solid sphere is going just a little bit faster than the hollow sphere. And so we expect the ball, the solid ball, to get to the bottom first. Let's check out how our results compare.
Ready?
Oh, this angle could be tricky. Let's check this again.
Which one's going to get there first? Take 2. Was that a fluke? Let's try one more time.
No fluke there.